All right, I want to put a few numbers to some things for you. This is going to be pretty short and pretty improvised, so hopefully I don't come up with any numbers that are like super crazy and cause me any problems there. I need to grab a little piece of paper here, write some of this stuff down. Um, so let's suppose I have an oscillation, and the mass of the oscillator is 0.25. The spring constant is 100. Okay, and those two things together are going to imply that my value for omega is 20, and then my period is going to be 0.3142. Okay, now let's let b equal to 1 or 0.1, just like that. And let's go ahead and calculate the value for gamma, which is the decay constant, not the damping coefficient. Okay, so the decay constant, let's write that in here, is gamma, which is b over 2m. Okay, so we're going to have 0.1 over 2 times 0.25. All right, and then, so that's 0.1 over 0.5, and so that turns out to be 1/5, which is 0.2. Okay, so there's my value for gamma. All right. Now, let's go ahead and figure out what would be my time constant in that case. Well, since we know the value for gamma, the decay constant, it's just 1 over that. So I got 1 over 0.2. So my time constant, tau, is 5 seconds. Okay. Now, I'll kind of show you what that means on a graph here in just a quick second. All right. Let's go ahead and also calculate the half-life while we're here. And what we said a second ago was that half-life was going to be the natural log of 2 over our gamma value. So we've got ln of 2 divided by, in this case, 0.2. All right. And I got to pull up my calculator to do that. So we need, where's my natural log? Oh dear. Okay. Oh, there it is. Okay. Natural log of 2. Oh, not, I don't know where that came from. Okay. 2 divided by, what was it? 0.2? I hope it was 0.2. We get 3.465. 3.466 rather, if we keep a few more digits. Okay. 6. There we go. Okay. And so let's take a look at some numbers that I ran using engineering folks. You guys will recognize this, using something called Octave. Okay, and I wrote a little program here. So I've got my mass, my spring constant, all my other descriptors, omega, F, and T. B, the way I wrote the program, it's going to ask for a value of B. Okay, it's going to calculate gamma, and then do the function, blah, 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 blah. Anyway, when I run this thing, okay, then I got to come in here and tell it our damping coefficient was 0.1. There we go. And so gamma is 0.2, and it's going to make a graph for us. All right, and I'm going to bring it over here so you can see it. Just like that. Okay, now put my graph over here. I'm going to collapse that. See if I can get this on the same page here. I can try to illustrate a little bit what's going on here for you. Okay. So gamma is 0.2. All right. So again, that has to do with the decay of this red line here. It's not a line. There's a red curve here. That's my decaying exponential. Tau is 5 seconds. So let's come over here. Let's see where we are. Here's 5 seconds. We're going to come up and see what value we've got right here. Okay. Look down here in this corner. Okay. So there's 5. I'm going to come up to the line as close as I can. All right, that's pretty close right there. 0.373 0.388. Okay, 0.37388. Now, I'm going to flip back to my, I'm going to write that down on the paper so I don't forget it. 0.37388. Okay, so I'm going to flip to my calculator. Back to my calculator. Here. Boom. Let's move that out of the way. And the number was 0.37388. Okay, and what I want to do is I want to flip that thing. Okay, so I'm going to go 1 over that. And see what I get there? 2.674. All right, now, if we go e to the 1 to get us the value of e, it's 2.718. Okay, so what the decay constant does for us is it gives us a number, in our case it was 5 seconds, a number that tells us how much time it takes for the oscillator to decay by E. Okay, so 1 over E is what we get to. So which is close to a third. All right, and so 5 seconds here. All right, we're at 0.38, whatever. Okay, whatever that number was I had a second ago. If we can nail it exactly, I don't know if we can or not. But anyway, it's pretty close. So that's what the time constant does for us. How much time it takes 1 over E. Now, if we go out 2 time constants, which would be 10 seconds in our case, then it would be one of these deals. 1 over E in the first 5 seconds and another 1 over E in the next 5 seconds. So then we'd be 1 over E squared. Now, if we went out to 15 seconds, it would go 1 over E, 1 over E, 1 over E, be 1 over E cubed. So every time constant, you can add another E on there. So if I go at 10 time constants, then I'm E to the 10th of where I was. Okay, so hopefully that makes some sense there. That's our time constant. Now, here's our half-life, okay? The time of our half-life was 3.466. So again, that's going to be right in here somewhere. I'm going to come up I'm going to try and hit 3.466. It's super hard to do. That's pretty close. Scooch up just a little. Anyway, you can see right there we're in the ballpark of a half. Okay, so our amplitude started at 1 and now we've cut down by a half. Okay. Now, if we go out 2 half-lives, instead of cutting by a half, it'll be cut by a quarter because it'll be a half of a half. If we got 3, then we'll be down to an eighth because it'll be a half of a half of a half. Okay, so it's 1/2 to the power of however many you've got. All right, so let me write that down. All right, because if you're like me, I'm kind of visual. I like to see it. So if I go 1/2 to the n, all right, that's what I'm going to be left with if we go in number of half-lives. Okay, so if we go out there at 3 half-lives and we want to know what's our amplitude, we can go 1/2 cubed, sort of like that. All right. Now, just one other thing I want to throw out here. I think because I think one of your homework questions had something like this. It's like, well, how many oscillations does it make? Okay, so we might say, for example, in 1 half-life, how many times has it oscillated? Okay, and that's really easy to do. We're just going to divide by the period because the period is how much time it takes to do 1 oscillation. Okay, and so we would go in here, we'd say the amount of time, 3.466, and we would divide by the time it takes to do 1 oscillation, 3.142. Okay, I got to write that down because I'm going to calculate it for you here in just a second. 3.466, we're going to divide by 0.3142. Okay, flip over to my calculator. I got 3.466 divided by 3.3142. Boy, that's kind of weird that's 1/10 of pi, isn't it? But it's just random. Okay, and we get 11. 11 there, so I'll write that down. Flip back here. Okay. And that, so anyway, that worked out to be 11. Okay. And so means by the time we get over here, we should have 11 oscillations. Okay. So down, up 1, down, up 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So there we are. The 3.4 is right in there. Okay. So it was pretty close to 11 exactly. Okay. Anyway, there you go. So I think in this kind of example, I hope it wasn't too random, but I think I hit everything that you're going to kind of need to know, in addition to the lecture stuff there, to be ready for your homework. Okay. Alrighty. There we go, guys.